Welcome to the deep dive. We're tackling a really unique vehicle today. I want you to forget the hyper-efficient electric sedan for a moment or, the high-tech fighter jet.
Yeah.
We are zooming in on a massive heavy-duty machine, the cement mixer truck.
Right.
Now, this isn't often considered the pinnacle of automotive tech, but when you really look at the complexity, integrating a massive diesel engine, a powerful 400-volt P2 hybrid motor, and a gigantic rotating drum full of sloshing, time-sensitive concrete.
It's one of the most demanding software challenges out there. Absolutely.
It's a safety-critical puzzle on wheels.
It really is. It's the ultimate convergence of mechanical inertia and real-time control. We are not just talking about managing two power sources.
No.
We are coordinating them in really severe operating environments, making sure it's stable when the center of gravity is constantly shifting, and, all the while adhering to the absolute maximum level of functional safety. ISO 26262.
SLD, the highest level.
The highest. And the control required is so specialized, particularly around the electric power takeoff system, the ePTO, which is just crucial for the quality of the concrete.
And that's what we're here to do. Today, we're translating an extensive strategic engineering report that's aimed directly at you, the learner, who needs a complete blueprint. Our mission is to establish the entire VCU, the Vehicle Control Unit Software Function Description process, from the ground up for this very specialized P2 hybrid vehicle.
Right.
We're extracting the architectural, the control, and the validation steps you need to build this capability.
And the documentation we analyze, it lays this all out very clearly. It all rests on what they call the 4 pillars. And these aren't optional guidelines, they are sort of strategic mandates for safety, for quality, and this is crucial in the commercial vehicle space for scalability. If you ignore any one of these pillars, you basically cripple the entire development process.
So let's lay that foundation immediately. Pillar 1, standardized architecture. This is absolutely non-negotiable, and it's driven primarily by AUTOSAR.
Then you have pillar 2, model-based development, or MBD. That defines the language of the VCU logic.
Pillar 3, built-in safety. This means ISO 26262 ACE-LD is the absolute bedrock from the very first line of the requirements.
And pillar 4, which honestly consumes nearly half the project time, continuous validation and verification, the V&V.
The V&V pipeline.
It establishes this relentless pipeline that starts with software testing and culminates in rigorous hardware-in-the-loop verification that simulates the brutal, real-world conditions of a construction site. The whole approach is geared toward managing these complex hybrid dynamics and ensuring those specialized controls, like the ePTO, function flawlessly.
Okay, let's unpack this blueprint, starting where every great system starts, the digital foundation. Why this software architecture has to be standardized, rigid, and just absolutely non-negotiable. So when you combine the complexity of a diesel engine, a 400-volt electric motor, all the high-speed power electronics, and those ACE-LD safety requirements, chaos is basically the default state.
It is. And to manage that chaos, to ensure long-term maintenance, the control system needs a standardized skeleton. And that is exactly the role of the AUTOSAR Classic Platform, or ACP.
So AUTOSAR is more than just a protocol.
Oh, much more. It's a philosophy. It dictates how the VCU software components are organized and how they interact. And its standardization is so critical for the heavy-duty sector because it ensures portability.
Portability.
Yes. If the VCU software is decoupled from the hardware via AUTOSAR, the manufacturer can potentially reuse those core control components, let's say the anti-jerk logic we'll talk about later, across a cement mixer, a dump truck, maybe even a mining vehicle, as long as they use the same standard interface.
Which makes the software investment scalable.
Yeah.
But for ACE-LD, you said the most crucial element is the isolation it provides. How does it actually achieve that compartmentalization?
It's all about its strict 3-layer structure. At the very top, you have the application software layer, the ASW.
This is where the magic happens.
This is where all the engineering IP resides, exactly.
Right.
The torque calculation logic, the energy management strategy, the thermal management controls, all of it.
And the ASW is made up of individual software components, or SWCs.
Exactly right. And these SWCs are the functional units. Now, here's a critical, non-negotiable constraint of AUTOSAR. The control logic within an SWC must never directly call an API from the basic software layer.
It's forbidden.
Strictly forbidden. It can't have any knowledge of the underlying microcontroller or the communication stack. And that isolation is what guarantees the safety segregation we need. If a fault happens in the low-level communication stack, it cannot corrupt the high-level torque control logic.
And the layer that enforces this rigid separation, that's the runtime environment, the RTE.
Think of the RTE as a customized operating system. It's generated specifically for this VCU's application. It's the virtual nervous system.
A traffic cop for the software.
That's a great way to put it. The RTE is responsible for all intercomponent communication, the sender-receiver ports for data, client-server ports for services, and, most importantly, it handles all the scheduling. It makes sure the various SWCs are executed at precisely the right frequency.
So 1 millisecond for torque control, but maybe 100 milliseconds for energy management?
Precisely. And critically, it provides that complete isolation barrier between the application layer and the hardware-facing basic software.
Which brings us to the bottom layer, the basic software layer, BSW, the one closest to the physical reality of the chip.
The BSW is broken down into stacks of services. You've got the MCAL, the microcontroller abstraction layer, which deals directly with the RX TC3XX's peripherals. Then you have the service modules.
Like the comm stack.
Right, the comm stack, which manages communication protocols, JADE 1939 for talking to the diesel engine ECU, that's the heavy-duty standard, and then standard CAN for talking to the inverter. You also have the memory stack, or NVM, for non-volatile storage.
Storing fault codes, system parameters.
All that crucial data, and of course the system services like the Watchdog Manager, the WDGM, which is absolutely indispensable for ensuring functional safety compliance.
Okay, so that's the architecture. Now let's pivot to the language used to actually write the VCU logic. Model-based design, or MBD. You said this shifts the entire development paradigm.
It does. MBD is where we enforce that strategic principle. The model is the specification. The code is merely the output.
I love that.
It eliminates the immense risk of misinterpretation that happens when a control engineer writes a text spec, and then a software engineer has to translate that spec into C code. With MBD, the control engineer designs the logic graphically in a tool like Simulink using a standardized approach enforced by guidelines like MAB.
So the Simulink models, along with the specialized AUTOSAR block set, they're automatically compiled into embedded C code using tools like Embedded Coder. What makes that automated process so powerful, especially in an ASIL-D context?
It's all about guaranteed traceability. Every single functional block in that graphical model has to map one-to-one to an AUTOSAR runnable.
A runnable being the smallest unit of execution.
The smallest. And that runnable then maps directly to a function call subsystem in the model. So if an auditor comes and asks, why is the motor generating 50 newton-meters of torque at this exact moment, we can trace the code back to the runnable, back to the function call subsystem, and back to the specific graphical control block that commanded it.
And the code itself has to meet standards.
Oh, absolutely. The reports mandate MinSOR C2012 compliance right from the start.
Let me push back on that for a second. Why insist on MIS-RSC rules?
Yeah.
I mean, aren't these just coding-style guidelines?
That's a common misconception. They are far, far more than style. They are safety requirements. Rules like prohibiting dynamic memory allocation, so no malloc or free, are crucial in real-time embedded systems.
Why is that?
If you allow dynamic memory, you risk fragmentation and unpredictable runtime behavior. You could have sudden, non-deterministic failures because you run out of memory, which is completely unacceptable for ASIL-D. MISRA rules also restrict things like complex pointer arithmetic and mandate explicit typecasting, which just eliminates entire classes of common, fatal embedded system bugs.
Okay, that makes sense. Now, that foundation needs a powerful processor, and we're talking about leveraging a multi-core microcontroller like the Infineon RX TC3XX family to handle the load. The challenge isn't just power, it's partitioning that power safely.
Absolutely. The multi-core strategy is essential for achieving two goals: brute compute power, and more importantly, safety isolation and deterministic execution. We have to assign tasks based on their priority, their required ASIL level, and their latency needs. The source material dictates a very highly optimized 3-core allocation.
All right, let's look at Core 0 first. This sounds like the heavy lifter.
Core 0 is designated the ASIL-D safety and control core. It handles the most time-critical tasks, the ones that require the absolute shortest interrupt latency to meet the fault-tolerant time interval, the FTTI.
So what's on there?
The main torque arbitration logic, the EGAS level 1 and 2 monitoring, and the active damping or anti-jerk control. The VCU is executing its core control loop on Core 0, often at a 1 millisecond frequency. Any delay here could lead to a loss of control that exceeds the FTTI, and that would result in an immediate system shutdown.
Okay, so if that's the cockpit, the mission-critical area, why put anything else on the other cores? Why not just use one really powerful core?
Because of the need for isolation, let's look at Core 1, which is the Comm and Diagnostics core. It's rated at ASLB or QM. This core is intentionally isolated to handle high I/O loads.
I see.
This includes the entire communications stack, all the incoming and outgoing CAN and J1939 messages, the diagnostics layer, and the XCP calibration services.
But wait, if Core 1 is handling all the J1939 communication, doesn't that introduce a latency risk for the data that Core 0 needs? Like the driver's pedal request or the engine speed, can you buffer that latency?
That's the critical trade-off. You hit on it. We accept a minimal measured latency when passing data between cores because the alternative is so much worse.
Which is?
The communication stack generates a massive, unpredictable stream of high-frequency interrupts. If Core 0 had to handle all of those interrupts, the jitter introduced would completely destroy the deterministic nature of that 1 millisecond torque control loop. So by isolating it on Core 1, we ensure that the high-frequency communication noise doesn't interfere with the ASIL-D critical real-time processing on Core 0.
And that latency is managed.
It's managed via highly deterministic intercore communication mechanisms.
Speaking of which, let's define Core 2, the energy and thermal core.
So Core 2 handles tasks that are computationally heavy but are physically slower in their dynamic response. This makes them suitable for an ASIL-B integrity level.
Like the energy management strategy.
Exactly. The complex EMS, the thermal management control loops for the battery and the motor, and the dedicated ePTO control logic. The inertia of a battery's thermal system, or the slow nature of optimal energy calculation, means these tasks can run at much slower rates, 10 milliseconds up to a second, which frees up Core 0 entirely.
So we have crucial data being calculated on Core 2, like the ideal torque split from the EMS that has to be sent to the torque manager running on Core 0. Since these cores are physically separated, how does the VCU safely and reliably communicate across that boundary without introducing race conditions or corrupted data?
That is the core function of the Intercore Communication Mechanism, or IOC, provided by the AutoSAR OS. This is a critical safety component. The reports mandate that all cross-core data exchange must strictly use IOC. The RTE generates specific communication objects, and it often leverages hardware features like dedicated memory partitions and synchronization primitives.
What does that mean in practice?
It might employ things like spin locks or lock-free queues to manage the shared memory space. This guarantees data consistency and prevents one core from overwriting data while the other is reading it. It eliminates a classic, really difficult to debug multi-core software safety hazard.
The brain is structured. We've isolated the safe core, the noisy core, and the strategic core. Now we jump into the logical execution. If the architecture is the skeleton, the torque path is the central nervous system. So how does this VCU actually decide what the truck should do?
The torque path management is the foundational sequence that governs all vehicle motion. It's a very disciplined, step-by-step process that has to be absolutely traceable, ensuring that the final output command is the safest possible interpretation of all the input requests.
Okay, let's follow that chain from start to finish. Step 1. The beginning of any motion, the driver torque request.
This starts with the input from the dual-channel accelerator pedal, the APP. Because this sensor directly dictates acceleration, it's an ASIL-D component.
So it's redundant.
Redundant, yes. The VCU must first parse the raw sensor values, apply some filtering, and most importantly, perform a strict plausibility check. It verifies that APT1 and APP2 are within a very tightly defined error band, say 5% deviation, and confirms the input is plausible. For example, the pedal isn't pressed while the brake is also active. Only then is the raw driver demand torque calculated.
Okay, next, that raw request gets modified by external requests. What kind of inputs are we gathering here?
Inputs from other controllers on the vehicle network. The Electronic Stability Program, ESP, or traction control might request negative torque to maintain stability. Adaptive Cruise Control, ACC, requests specific torque to maintain distance. And crucially, the Transmission Control Unit, the TCU, will send shift protection requests.
Which is a torque reduction.
Exactly, commanding a temporary, very precise torque reduction during a gear change. This is to reduce shock and protect the physical driveline components, the clutch, the gears, from damage.
With all those requests gathered, the VCU has to perform the key function of a hybrid coordination.
This is where the strategic EMS, running on Core 2, provides its results. The EMS determines the optimal split factor, deciding exactly how much of the final arbitrated torque should come from the internal combustion engine, the ICE, and how much from the electric motor. This decision immediately dictates the current hybrid operating mode,
EV, parallel assist, or something else.
be it EV, parallel assist, or load point shift. Correct.
And before sending the final command, we hit the safety check, limitation, and safety.
Every single calculation is bounded by protective envelopes. This is the last chance to apply constraints based on real-time physics. Are we exceeding the thermal limits of the motor or the inverter? Is the battery state of charge, the SUSC, too low to contribute or too high to accept regeneration? And most critically, this is where the e-gas safety limits derived from that redundant level 2 monitoring path are imposed.
And the ultimate output is the final torque command, separated into two distinct channels, one for the engine, one for the motor.
That's right. TIC sent via J1939 to the engine ECU, and TS sent via CAN to the high-voltage inverter.
So what if the driver requests full power, say plus 500 Newton meters, but the TCU simultaneously requests a reduction to 0 for a shift, and the ESP requests minus 100 for stability? That conflict is unavoidable.
And that unavoidable conflict requires the torque arbitration hierarchy, which is structured as a very rigid priority pyramid.
This hierarchy sounds like a blend of a winner-takes-all system for the primary demands, but it's bounded by a limitation envelope for protection. What holds the absolute veto power at the very peak?
A-cell D safety interventions, no question. This includes the highest priority functional safety intervention, the e-gas cutoffs we'll detail later, and any stability request that originates from ESP or ABS.
They have absolute veto power.
Absolute instantaneous veto power. If the primary torque command risks a rollover or a slide in a fully loaded high center of gravity vehicle like this, that command is immediately and unconditionally overridden by the stability system.
But if the system prioritizes ESP intervention over a driver's pedal request, doesn't that make the driver feel, I don't know, disconnected from the vehicle? How do you balance that safety requirement with the need for driver confidence in these heavy-duty environments?
That is a key calibration challenge. The intervention has to be calibrated to be minimally intrusive yet maximally effective. Heavy-duty vehicle drivers, they understand that stability is paramount. So the VCU has to manage the transition between the driver request and the safety intervention using carefully controlled torque ramp rates.
So it feels predictable.
Exactly. So the driver feels the intervention is necessary and predictable rather than just jarring. But the core principle always remains. Safety trumps feel.
Okay. Moving down the pyramid, what governs the preservation of the physical asset, the truck itself?
That would be the mid-level safety and protection, typically A-style C or B. This includes TCU shift protection, which prevents mechanical damage to the gearbox, and AEB, automatic emergency braking, requests for rapid negative torque. Below that are the system protection limits, dynamic power limits based on battery SOA, motor temperature, or even high-voltage insulation integrity. These limits enforce the protective operating zone for the electric system.
And finally, the lowest rung handles the primary driver experience.
That's where you find ACC, standard cruise control, and the filtered driver demand. And at the absolute base is idle speed control, just the minimum torque required to prevent the engine from stalling. It's important to see the arbitration layer as a series of nested min-max selectors. Regardless of what the driver asks for, the final command is guaranteed to be within the protective envelope set by the highest priority safety and protection constructs.
And the coordination of these two power sources is formalized in the hybrid mode state machine, which is typically modeled in state flow to define deterministic transitions between modes. Let's explore the strategic rationale for the key operating modes.
Okay, starting with EV mode, pure electric driving. This is essential for operation in sensitive areas.
So what are the preconditions for going into EV mode? It can't just happen anytime.
No, there are strict conditions. First, the battery SOS has to be healthy, perhaps greater than 30%, to ensure you have sustained operation. Speed has to be low, typically less than 30 kilometers per hour, which is suitable for maneuvering on a construction site. And the torque request must be well within the motor's continuous power capability.
The goal is simple.
Zero noise, zero local emissions. In this mode, the P2 clutch opens, the diesel engine is off, and the motor provides 100% of the tractive effort.
Next up, parallel assist, when both power sources are working at the same time.
This is triggered when the total required torque exceeds what the engine can efficiently provide on its own, or when a very rapid response is needed. The engine is running, the clutch is closed, and the motor is assisting. This is often necessary for rapid acceleration, at kickdown, or, importantly for this vehicle, when the high-load ePTO is active. The electric motor is excellent at filling that torque gap, the turbo lag, while the massive diesel engine spools up to full power.
The mode that reveals the strategic genius of the EMS is load point shift, or in-transit charging. Why would the VCU intentionally command the engine to run slightly harder than necessary during a cruise phase?
Because it's maximizing long-term efficiency and doing strategic preparation. When the truck is cruising, the VCU might identify that the engine is operating slightly off its best specific fuel consumption island, its most fuel-efficient point.
I see.
So the VCU artificially increases the load on the engine, shifting its operating point onto that BSFC island. The resulting excess mechanical torque is then immediately absorbed by the P2 motor, which acts as a generator, efficiently charging the HV battery.
So you burn fuel slightly more efficiently now, in transit, to pre-charge the battery for later use on site.
Precisely. It's a proactive cost function. You're investing a little fuel now to ensure you have the energy reservoir needed for a prolonged, silent, high-load ePTO operation on the site later. This pre-charging is a cornerstone of the adaptive rule-based strategy we'll touch on, linking cruising behavior to operational requirements.
And the final state is regenerative braking.
Recovering kinetic energy, standard practice for any hybrid. The motor generates negative torque. However, the VCU has to constantly monitor the battery's constraints. If the battery is cold or the SOSI is approaching, say, 90%, the battery's charge acceptance current plummets.
And you can't just keep pushing energy into it.
You can't. If the VCU continues to force regeneration, the resulting overvoltage could damage the battery or the power electronics. In such cases, the VCU must dynamically hand the braking request back to the friction brakes and exit regeneration.
Before we transition to the specialized cement functions, we absolutely have to elaborate on the active damping or anti-jerk strategy. For a heavy-duty vehicle, this is a massive comfort and stability solution that's enabled entirely by the hybrid design.
It addresses the mechanical reality of massive rotational inertia. When a fully loaded cement mixer starts or shifts gears, the long drive shaft and huge vehicle mass combine to create a low-frequency oscillation, that dreaded 2 to 5 hertz shuffle.
I can picture that.
For the driver and the chassis components, it's highly uncomfortable, and it puts stress on the entire driveline.
It's that feeling when the whole truck seems to buck slightly, a low-frequency shudder you can't manually smooth out. So how does the VCU software become a mechanical damper?
It utilizes the millisecond-level responsiveness of the electric motor, which far, far exceeds the slow dynamics of the diesel engine. The VCU first monitors the speed difference between the electric motor and the wheel speed, which indicates if the driveline is winding up or releasing.
And then it isolates the offending frequency.
Yes. A bandpass filter is applied, and it's specifically tuned to the known mechanical resonance range, say 2 to 8 hertz, isolating only that oscillatory component. Once it's isolated, a compensation torque damping is calculated, usually using a PID or a lead-lag compensator that's tuned specifically for damping.
So the calculated damping is an instantaneous corrective torque.
Correct. And it is overlaid onto the final motor command. The formula is basically TE-hem final T-arbitrated damping. So if the driveline begins to wind up, the filter identifies the oscillation, and the motor applies a tiny instantaneous negative counter torque to immediately absorb that energy. If the driveline releases too quickly, the motor applies a quick positive torque.
It smooths the entire mechanical system out instantly.
Exactly. It provides a level of refinement that was previously just impossible in heavy-duty vehicles.
That's a beautiful synthesis of software and mechanics. Now let's move to the features that are unique to this machine, functions dictated by the very job of mixing concrete.
A cement mixer is fundamentally a mobile production facility. Its primary job is delivering concrete of a consistent quality. And that reliance on quality requires the ePTO constant speed control system to achieve complete decoupling from the chassis engine.
Why is constant drum RPM so critical for concrete quality? I would think a little variation wouldn't matter.
Oh, it matters a great deal. Concrete is perishable. If the rotation speed fluctuates because the chassis is accelerating or braking, the material consistency can be compromised. Fluctuations can lead to segregation, where the aggregate separates from the cement, or, in extreme cases, premature solidification.
So the old way was a problem.
Traditionally, the drum was hydraulically linked to the engine, which meant drum speed varied with engine speed. The electric ePTO decouples this entirely.
The goal is to maintain, for example, a strict 2 RPM for transport, or maybe 10 RPM for agitation, regardless of the truck's road speed or engine status. How does the VCU ensure that precision control, especially when the load inside the drum is changing and nonlinear?
It requires a highly robust control scheme. Front feed and feedback, PI control. The PI feedback loop handles the standard error correction, but the magic, the reason for the precision, lies in the feed-forward term.
The feed-forward term.
Yes, the VCU monitors the electrical input to the ePTO motor, the current, the voltage, to estimate the load resistance.
Estimate the load torque. Why not just measure the speed and react?
Because the load resistance is dynamic. The concrete's viscosity, its slump, changes with time, temperature, and even the geometry of the drum. If the VCU simply waited for the drum speed to drop before the PI controller reacted, the control would be sluggish and reactive. By estimating the load, the resistance caused by the concrete itself, the VCU can preemptively inject the necessary torque to counter that load before the speed deviates.
So it's proactive.
It's proactive. It maintains the strict RPM requirement even when the concrete viscosity changes.
And this precision control enables a safety and operational imperative, the stationary generation mode, or parking charge. This happens when the truck is idling on a site for a long period.
This scenario comes up all the time. The truck is waiting, perhaps to offload, and the battery starts drops below the critical 20% threshold needed for sustained ePTO operation. The VCU has to take proactive steps to ensure energy security.
What is the choreographed sequence the VCU executes?
First, the VCU requests neutral from the TCU, ensuring the wheels are decoupled. Once neutral is confirmed, it automatically starts the diesel engine. And critically, it commands the engine to run at its optimal BSFC speed, for instance, 1200 RPM, even if the actual required speed for just idling would be much lower.
I see.
The P2 motor then acts purely as a generator, absorbing the engine's efficient mechanical output.
So the engine is running only to make electricity?
Exactly. And that generated high-voltage power simultaneously feeds the actively mixing ePTO system, keeping the concrete churned, and it charges the HV battery. It's a structured, efficient energy maintenance cycle designed to ensure the truck never runs out of power while on site.
This brings us to the broader strategic challenge, the energy management strategy, EMS dilemma. For heavy vehicles, the choice of EMS is a huge architectural decision with massive ramifications for testing and verification. The two classic choices are rule-based and ECMS.
The rule-based strategy, it relies on a lookup table and state machine logic. If speed is X and torque is Y, use Z% electric assist. Its enormous advantage is its determinism.
It's predictable.
It's transparent, it's easy to calibrate, and its logic paths are straightforward to verify, which is highly, highly desirable for ISO 26262 and S-BICE compliance.
But the drawback is that it's inherently suboptimal, isn't it?
Right. It's not globally optimal because it operates on fixed rules that must be painstakingly tuned for every single work cycle, highway cruising, stop-and-go urban construction site operations. Then you have ECMS, the equivalent consumption minimization strategy.
The theoretical darling of hybrid optimization.
It is. ECMS is constantly solving a cost function, minimizing the combined cost of fuel and the equivalent battery energy. It's adaptive, leading to a theoretical 5 to 10% improvement in fuel economy. However, it imposes immense engineering costs.
Like what?
High computational load, extremely complex calibration of the critical equivalent factor parameter, and critically for ASIL-D, its non-deterministic, optimized nature makes comprehensive safety testing and verification exceptionally difficult and time-consuming.
Given those high stakes, the reports recommend the pragmatic solution, adaptive rule-based.
This is the optimal engineering compromise for commercial vehicles. It retains the verifiable, deterministic safety of the rule-based foundation, but introduces an adaptive layer on top. And this layer is the work condition identification module.
How does that module operate? What data is it analyzing to identify the vehicle's strategic state?
It's analyzing dynamic data over time. Continuous GPS data, speed profiles, time on-site counters, and recent ePTO usage intensity. By clustering this data, the VCU can classify its operating state. Is it in high-speed cruise, or is it in construction site operation?
And once it identifies the state, it dynamically adjusts its EMS goals.
Precisely. If it identifies high-speed cruise, the VCU's strategic goal proactively shifts to maximizing the target SAC. It will initiate that load point shift mode we talked about more aggressively. The goal is to arrive at the site with a full energy buffer. If it identifies construction site operation, the goal shifts to maximizing EV mode usage and ePTO operation to meet the requirements for reduced noise and local emissions.
It becomes a strategic planner.
This predictive layer transforms the EMS from just a reactive tool into a strategic planner.
That strategic foresight is a testament to the system complexity. But no matter how smart the BCU is, if it's not safe, it's unusable. Let's look at the bedrock, the functional safety architecture.
ISO 26262 is the entire constraint envelope for the system. Achieving ASIL D means every decision, every line of code must be made with the absolute prevention of hazardous failures in mind. The core safety philosophy underpinning the entire torque control is no limp hold.
That phrase needs to be understood in the context of a 40-ton vehicle with enormous inertia. What exactly does no limp hold mean?
It is the mandate that the system must never maintain the last known torque command if a fault is detected. Imagine the high inertia of a fully loaded truck. If the VCU detects a pedal sensor error and simply holds the last known torque request, say 500 newton meters, that results in prolonged unintended acceleration. That's catastrophic.
Instantly dangerous.
The VCU must immediately and rapidly revert to a safe zero torque state known as torque cut or freewheel. The entire system is built to ensure the fault-tolerant time interval, the FTTI, which might be 200 milliseconds, is never ever exceeded.
And to guarantee this rapid reversion to safety, the system implements the EGAS 3-layer monitoring architecture, which provides constant, redundant oversight over the torque command path. Let's start with level 1.
Level 1 is the functional control path. This is the VCU's main brain, the SWC torque manager we discussed in Section 2. It contains all the complex control algorithms, the full hybrid dynamics model, the detailed arbitration logic, and critically, we treat this complex layer as untrusted.
Untrusted. Why?
Because its very complexity makes it the most statistically likely location for latent software bugs or transient hardware faults.
So level 2 exists to monitor the complex level 1 with something simpler and therefore safer.
Exactly. Level 2 is the functional monitoring path. It runs independently using separate processing resources, ensuring strict segregation from level 1, and level 2 performs two key functions. First, program flow monitoring, verifying that level 1's runnables are executing exactly when and how often they should. If level 1 misses its 1 millisecond deadline, level 2 detects it.
And the second function is the torque check itself.
The torque plausibility check. Level 2 uses a highly simplified independent physics model, something much less complex than the level 1 hybrid model, to calculate what the permissible torque should be, based only on the raw sensor inputs like pedal position and current speed. It then constantly compares this simple, verifiable calculation against the complex request from level 1.
So if the complex path deviates too far from the simple, independently verified path, the system assumes level 1 is compromised.
Correct. If the deviation exceeds a defined maximum threshold, say 50 newton meters, and persists longer than that 200 millisecond FTTI, level 2 immediately triggers the VCU safety state, enforcing the torque cut.
But what if the entire microcontroller locks up? What if the software completely runs away, preventing both level 1 and level 2 from executing? That's where level 3, the controller monitoring path, the hardware guardian, comes in.
This is the ultimate physical failsafe, and it's independent of the VCU's software execution. Level 3 involves the interaction between the main microcontroller and an external watchdog timer, often integrated into a dedicated power management IC, or PMIC. It operates via a challenge response mechanism.
This sounds like a security protocol designed for hardware. How does it work?
The external watchdog periodically sends a randomized signal, a challenge or a seed, to the VCU. A tiny, highly verified segment of the level 3 logic within the VCU must instantly process this seed using a specific algorithm to compute the correct response, or key. This response must be returned to the watchdog within an extremely tight time window.
So if the VCU is running normally, it responds correctly and on time. But if the main program loop freezes, or a catastrophic failure prevents software execution,
the watchdog times out or receives an incorrect response, and since the watchdog is a separate hardware-enforced chip, it immediately assumes the VCU is unreliable. It then uses independent physical hardware lines, not software signals, to trigger the final safety cutoff path.
a physical cutoff.
This physically cuts the power relays to the fuel injectors for the engine and the IGBTs for the high-voltage inverter, ensuring the 400-volt system cannot produce any torque. This is the absolute guarantee of that no-limp hold philosophy.
That is a comprehensive defense. Let's look at how the HERA analysis translates into specific mitigation requirements. SGO1, prevention of unintended acceleration, ACLD.
The hazard here is the truck suddenly accelerating without any driver input. The safe state is zero torque. The VCU must command the inverter to shut down the IGBTs. Furthermore, because some motor failure modes can generate huge back EMF voltage, especially in a 400V system at high speed, The VCU must be prepared to trigger an active short circuit, ASC, to safely dissipate that energy and prevent damage or secondary faults.
Next, the hazard specific to the job, SGO2. Prevention of unintended drum rotation, AZLC.
This is all about protecting personnel working near the truck's discharge chute. If the ePTO motor were to accidentally start or reverse, it's an immediate mechanical hazard. The safe state requires absolute physical prevention of rotation.
How do you do that?
Mitigation involves redundant layers. A software-enforced rotation lock combined with a hardwired safety signal from the discharge chute safety interlock switch. That switch provides a mechanical, independent ASLC layer of redundancy.
And finally, SGO3. Prevention of unintended deceleration or lockup, also ASLC.
This addresses the risk of excessive negative torque, too much regeneration, especially during high-speed cruising. If a fault causes the motor to generate a huge, unplanned braking torque, it could cause wheel lockup and instability. So the VCU must immediately open the high-voltage contactors to decouple a battery or trigger the active short circuit, stopping the regeneration and allowing the vehicle to freewheel safely without losing steering control.
The software has to be flawless, and the process to build it must be rigorous. Which brings us to the final and perhaps most time-consuming strategic pillar, verification and quality assurance.
The V&V framework operates on the principle of left-shift validation, pushing validation as far left or as early in the development timeline as possible. This starts with testing the model itself, not just waiting for the code.
We begin with MIL, model-in-the-loop, and SOIL, software-in-the-loop testing. The strict quality constraint here is achieving modified condition decision coverage, or MCDC.
For ASLD modules like torque arbitration or e-gas monitoring, the requirement is immense, greater than or equal to 90% MCDC coverage. This is a primary driver of cost and time to market. MCDC ensures that in every complex logical decision, like IF A, ND, B, or RC, each individual condition A, B, and C is shown to independently affect the final true or false outcome.
Why is that independence proof so strategically important for safety?
Because it proves that there are no untested, hidden, or dead paths in the safety-critical logic. This is essential for building the final safety case argument for ASIL-D certification. And this is why model-based design is a strategic necessity. Generating the code automatically, combined with specialized V&V tools, makes achieving and documenting this high coverage feasible. If you tried to achieve 90% MCDC on manually written C code, the time investment would be prohibitive.
We also use back-to-back testing at this stage.
That's the crucial check to ensure the code generation process itself didn't introduce errors. We compare the results of the MIL simulation, which runs on high-precision floating point numbers, against the SIL test, which runs on the generated C code using the target's fixed-point numerical precision. Any numerical deviation outside a defined tolerance means the code generation process failed, and the model or coder settings have to be adjusted.
Once the code is proven robust in the software environment, we move to the final critical stage, hardware-in-the-loop, or HIL verification. This is the ultimate virtual stress test, where the real VCU is tricked into thinking it's controlling a truck on a dangerous slope.
The success of HIL, typically run on platforms like bSpace, hinges entirely on the quality and complexity of the plant model. For a heavy-duty vehicle, we need far more fidelity than a simple passenger car model.
What are the specific requirements for this high-fidelity plant model?
We require a 14 degrees of freedom vehicle dynamics model. We're not just simulating acceleration and braking, we must accurately model pitch, roll, and yaw behavior under dynamic load shifts to validate the ESP and ABS interactions. The high center of gravity in a fully loaded cement mixer means dynamic stability is always precarious.
And central to the entire VCU function is the physical reality of the concrete itself. You need a dedicated concrete load model.
This is a major factor, often underestimated in standard vehicle models. The concrete load model simulates the nonlinear resistance and mass shift based on factors like the concrete's slump or viscosity, its density, and the drum RPM. The output of this submodel is vital. It calculates the precise load torque on the drum and, most critically, the resulting rolling moment exerted on the chassis as the mass shifts.
Why is that rolling moment output so important for validation?
Because the rolling moment feeds directly into the simulated 14DOF chassis model. We use it to validate how the VCU's torque arbitration logic interacts with the stability control systems during a dynamic maneuver. For example, a hard turn with a shifting concrete mass. We need to prove that the VCU can maintain stability and safety despite these extreme internal dynamic perturbations.
Okay, let's run through the high-impact HIL test cases provided in the reports, the ones that really stress the system and prove its safety integrity. The first is the full load slope start can interrupt.
Okay, picture the scene. A fully loaded truck, 12 cubic meters of concrete on a punishing 30% incline, completely stopped. The driver begins to accelerate. At the precise moment maximum torque is requested, the HIL simulator physically cuts the high-speed CAN link between the VCU and the inverter.
The expected outcome is not continued motion, but rapid safety.
Absolutely. The VCU has to detect the communication timeout within the FTTI, immediately recognize the inability to command torque, and execute the safe state, triggering the electronic parking brake request via the chassis control system. This prevents the vehicle from rolling backward and demonstrates correct, coordinated failure detection and response.
Test case 2, high-speed emergency stop.
The truck is cruising at 80 kilometers per hour on the highway. An external emergency stop button, maybe located near the rear discharge chute for site personnel, is pressed. This is a hardwired safety signal.
What multi-domain coordination must the VCU perform instantly?
It's a rapid sequence shutdown across both high and low voltage domains. Immediate engine shutdown, motor freewheel, the opening of the high voltage contactors to decouple the battery, and the instantaneous stop of the ePTO system. This tests the coordinated execution of every level 3 safety cutoff path simultaneously.
And finally, the classic sensor failure test, pedal sensor drift.
The scenario involves the two redundant accelerator pedal sensors, APP1 and APP2, slowly diverging. APP1 is correct, but APP2 drifts outside the 5% plausibility band. The expected outcome. The Level 2 monitoring path must immediately flag the plausibility fault. The VCU cannot trust the driver's request. It must transition to a controlled limp home mode.
Why limp home instead of immediate shutdown?
Because immediate shutdown risks stranding this massive vehicle in traffic. Limp home mode restricts the maximum available torque and limits vehicle speed, say, to 20 kilometers per hour, allowing the driver to safely navigate the truck to a service area or off the road while still maintaining essential functions like power steering and braking assistance.
To manage and repeat these rigorous stress tests, software quality can't be left to chance. It has to be automated via a CI/CD pipeline and quality control system.
The pipeline is the strategic gatekeeper, often managed by systems like Jenkins, enforcing ASPICE compliance through automation. As we noted earlier, strict MAN-RAC compliance is enforced by static analysis tools like Polyspace or Axivion before the code is even built. The pipeline checks for the exclusion of dynamic memory allocation and prohibits complex pointer operations, guaranteeing robustness from the lowest level.
So the code has to pass through a meticulous stage gate process. Code commit, then model check, code generation, static analysis, build, unit test, SIL, and finally HIL regression.
And if any gate fails, the code is rejected, and the merge to the main development branch is prohibited. This automated process ensures the complete traceability chain is maintained and verified at every single step. The requirements specification leads to the model, which generates the code, which passes all the tests, providing the necessary documentation for ASIL certification.
This has been an incredibly deep dive, moving from the strategic architectural decision to partition tasks across 3 microcontroller cores, all the way down to a calculated damping torque designed to eliminate a 2 Hz physical shuffle. It truly underscores the hidden complexity of modern heavy-duty vehicles.
The core value proposition, as summarized by the reports, is that this detailed function description is not just a specification for one truck. It is a blueprint for a robust, reusable platform. By building upon those 4 strategic pillars, AUTOSAR as the backbone, MBD as the language, ISO 26262 ASIL-D as the safety baseline, and ASPICE as the process constraint, the manufacturer creates a highly scalable, heavy-duty hybrid control capability.
That scalability is the ultimate goal here. The complexity forced by the cement mixer application, the high safety requirements, the nonlinear load, the specialized ePTO control demands a comprehensive, high-integrity design. That design, once it's proven, can be rapidly adapted for diverse commercial fleets like refuse trucks or mining haulers.
And that drastically accelerates time to market while guaranteeing safety compliance across the entire portfolio. This sophisticated approach ensures that the resulting VCU platform is capable of managing the most aggressive efficiency targets and operational demands in the heavy-duty sector.
And the final thought I want to leave with you focuses on that sophisticated energy management strategy. If the VCU can strategically decide when to charge the battery during a steady highway cruise phase, intentionally investing fuel, then just to ensure completely silent zero-emission ePTO operation on the worksite later. What seemingly simple, non-safety critical decision are you making today that needs a more sophisticated long-term strategic model? Managing a heavy, shifting concrete load dynamic forces this level of predictive brilliance into the software.
An excellent point of reflection. The physical constraint forces the engineering strategy.
That's it for this deep dive. Thank you for joining us as we explored the blueprint for automotive software excellence in the heavy-duty hybrid world.